start recording. Okay, folks, welcome back. Let's see here. Go through our usual list of announcements and then get started with lecture for the day. So, in terms of announcements, hopefully we've all completed the third homework by now. In case you haven't, then maybe do that today, or sometime in the next 2.5 weeks. But you know, the dirty secret here is if you go to Chris's office hours today, which I'm going to advertise, then you'll probably be the only one, and he'll just sit and do it with you. As Axel, came to my office hours the other day, and I didn't do it for him, to be fair, but we worked through problems, and he got a lot of personal attention. So anyway, just a hint to getting lots of professor help in a tough grad level class. Other than that, your midterm is next week. I saw a question on Piazza that I forgot to respond to. I don't think the student is here that asked it, but in any event, they asked what it covers, and everything up to and including Tuesday's lecture next week is what we'll say for the midterm. And everybody needs to be reminding me and Chris to actually write a midterm, since, as we've seen with these stupid mini quizzes, we are both prone to forgetting. And speaking of which, that'll be posted in the next hour or two. Yeah, so that's about it. As usual, the cadence in this course is pretty straightforward. The course itself is hard, but the rhythm is pretty easy. Any questions about organizational stuff before we get started with math? No? Okay, fantastic. Let me triple check that this camera's actually doing anything. I'm suspicious. No, it says it's recording. Okay, right, so our goal today is to finish off root finding and then talk about one-dimensional optimization, and then we're going to stop there. So in my mind, that won't take the entire hour and a half, but as a challenge to myself, it should take the entire hour and a half, because it wouldn't kill me to slow down in this class. But that's our goal for today. So we're going to wrap up root finding by talking about our first example, this is very exciting, of a quasi-Newton algorithm, which is a buzzword you may or may not have seen in numerical software. It's a very common one. So we're going to see what that looks like, specifically for root finding. And the reality is that the root finding version of quasi-Newton is actually somehow a little bit easier than we'll see for optimization. But it's also going to motivate the calculations we do for optimization, which require a little more heavy-handed math. In particular, I just posted, by the way, the optimization chapter of the book in the Piazza, I don't know, or whatever it is. Wow, that beeping is distracting. On Canvas. I don't know if anybody actually reads it, but it does include all the relevant calculation. I would, if you are reading the book, and I would strongly encourage you to, because you might have noticed it basically very closely covers what we do in lecture here. The optimization chapter, I basically rewrote most of it, specifically for this class. I threw out a big chunk of that chapter. That means two things. One is that it should align better and contain some more modern material. The other is that it may contain new and exciting typos. And remember, if you're looking for extra credit at this course, one way to get it is to identify typos in the textbook. So do let me know if you come across anything. In particular, for those of you who are following on the internet and only have access to the first edition, my bad, that's how it goes. The derivation of the BFGS algorithm in the first edition of the book is correct, but it's really clunky. And so in this version, I threw out that entire proof, and I tried to write another one. And this one is a lot cleaner. So we'll step through that in the next lecture or two. Yeah. There's also, what else did I fix? I fixed a bunch of stuff. I wasted a bunch of time on that chapter. Anyway, optimization is a topic that is very close to my heart, so I wasted too much time playing with the exposition there. Okay, so in any event, remember that our basic task that we considered in our previous lecture is root finding. And the basic goal here is that we're given access to some function f of x. And what we want is x star such that f of x star is approximately equal to 0. If you recall, by the way, as you review for your midterm, we already talked about conditioning for this problem. Remember, that was actually our very first example of conditioning, so I'd look back there. But we motivated a few algorithms in our previous lecture for doing this mostly in one dimension, right? Our first one was bisection, where we just in 1D identify some region where we think there's a root, and then we just keep chopping it in half. And then we motivated probably the world's most famous numerical algorithm, as they go, I suppose it can, Newton and Gauss kind of compete for this one. But the Newton's method here for root finding is nothing more than linearizing our function and then solving the linear root finding problem on the approximation and iterating, right? And the nice thing about Newton's method is that it converges quadratically in many cases, but of course it's predicated on converging at all, and sometimes it can diverge if you initialize it far away from your starting point. Okay, so there were some challenges with Newton's method, and the main ones really, which I've cleverly removed from my slides here, are that essentially, remember how Newton's method works. Essentially what we do is some iteration that looks something like x, what is it, a minus df x inverse times, oops, wait a second. It's f prime over f. Wait, sorry, I'm confusing it with the optimization version. Something like that, up to sign. Okay, and there were a few different headaches with this formula, or whatever the correct version is, that I really should have in my notes. I do have it in my notes, it's right here. Yeah, this is right. Okay, good. You'd think after, what, approximately 20-year career in numerical methods, I could remember Newton's algorithm because it's one line, but that is not the case. In any event, we have this iteration here, and there's one giant headache, which is this object, right? And in fact, in some sense, this is actually two headaches in one. One of the headaches is the fact that I have to compute this big derivative matrix. I can't prefactor it because it changes in every iteration. So like I'm stuck doing a different instance of Gaussian elimination from the start every time. And moreover, right, so there's this inverse part, which is annoying, and there's the computing the derivative itself, which is a big matrix, is n by n, right? And so neither one of these is particularly fun, and that was our motivation for this new algorithm that we're going to talk about, which is Broyden's method, right? So to bring us up to date with the theory from our last lecture, essentially what we're going to do is approximate df with some matrix that we call J. And J is some approximation of the Jacobian, that's why it's a J, of the function at x, right? And we went to all this work in the first half of our lecture deriving all these one-dimensional algorithms. And in particular, remember in 1D, we switched from Newton's method to something that was similar to Newton called secant, where essentially we kind of use lines through previous iterates to approximate derivatives. And the question was whether we can do a secant-like thing in multiple dimensions, right? And the problem was that secant only kind of tells you information about a line through the previous iteration and the current one. And that's not enough to make a whole n by n matrix, right? So we have to do something a little more complicated. So as a bit of review, what did we do? Well, we motivated a particular object called the directional derivative, which is essentially just the product between the Jacobian and a vector. And that gives us the difference between the function and two infinitesimally close points along V, right? And so that led us to this approximation here, which is to say that if I take the Jacobian of f and I evaluate it at xk, and I sort of multiply that by the difference between xk and xk minus 1, then I expect that to be roughly the difference between f at xk and f at xk minus 1. Notice this is like dy dx. It's just we move like the dx to the left-hand side. But because dx is now a positive and finite thing, of course, this is an approximation. Okay, and the problem is that this tells us, I mean, remember our unknown when I write this here? What is it? It's j. It's not the x's or the f's, right? And j has how many unknowns in it if I'm doing root finding in Rn? N. That's exactly right. Thanks, Paul. No, it's not. It's n squared. Right, because J is a matrix. Sorry, I really want to agree with you guys. I just want to be friends. No, but there's n squared unknowns in J because it's a matrix. It is most certainly not symmetric. We are not doing optimization right now. This is root finding. Jacobians can be not symmetric. Hessians are symmetric. Yeah, so Jacobians of gradient. Anyway, this is exactly what you just talked about in my office literally like 30 minutes ago. Yeah. But I digress. Right. So there are n squared unknowns in J, but how many relationships do I have? Well, this is like matrix times vector equals vector. So there's one relationship per row. So I have n squared unknowns, but I only have n relationships. So this is not enough to recover J. So in Broyden's method, what we do is we approximate J in a particular fashion we're going to mention, and then we kind of just follow Newton other than that. And in particular, here is the approximation we're going to use. That we're going to keep j along with our current iterate. So now we have kind of two objects that our code maintains per iteration. One of them is the x, which gets closer and closer to the root. And then the other is a matrix, which approximates the Jacobian at x. Does that make sense? And then what we're going to do is we're going to say that, like, okay, this secant condition, notice that we've written in the constraint here, right? This is a piece of information we know about j, but it's not enough to recover j. So to recover the rest of it, we're just going to say make j as similar as possible to the previous j, because we don't know anything else better to do. It's really as simple as that. Does that make sense? Now, writing it like this is not super useful, right? Because, like, well, for one, we haven't talked about optimization yet in this class. So, like, this is like yeah, like, great, this is a model. But it turns out, of course, that this problem, this particular optimization problem, can be solved in closed form. And so that's where our story ended in our previous lecture. And now our goal is to actually solve it. That make sense? Any questions so far? Yes? Why do we think this? And sometimes we don't. It's a good question. It's actually a totally reasonable one. All we can say is this thing is like the Jacobian along this one-dimensional axis, right? The one from xk to xk minus 1. Like they're like, assuming that xk and xk minus 1 are pretty close to each other, then like it really is the Jacobian. That product is correct. So the best intuition here is, like, let's say that I'm doing my optimization. I'm in Rn. I'm trying to find the minimizer. You know, I'm bouncing around. Maybe these are the x's. I kind of curl. And slowly it begins to converge on a point, right? Then over the last few iterations, that constraint is pretty close to like a reasonable one in a one-dimensional thing. So if you're lucky, we might not be, then what you'll end up with is, like, the last few iterations kind of see different pairs of xk and xk minus 1 that are observing Jacobian multiplied in that particular direction. So kind of over time, the algorithm accumulates a reasonable Jacobian. This is a model. I mean, this is a very heuristic object. It's actually quite hard to show that this thing should converge. It often doesn't. And so, like, I think actually there's a term that gets used a lot. We'll talk about it later, which is that the Jacobian will go stale. And the basic idea here is that, like, the Jacobian after like 50 steps somewhere down here still includes this little piece of information somewhere in it, like some little remnant of that. But, like, this divided difference really has nothing to do with the data there. And so a very common practice is to just every once in a while throw it away and start over. And in fact, we'll see that there's a really clever algorithm called limited memory quasi-Newton algorithm. The farther we get in this class, like, the more cool, like, bar trivia terms you get to learn, which does precisely that. It says that I'm always going to construct j from the last, like, L steps. Great question. Any other? Okay, so sadly for us, our task is clear. We need to write a formula for this thing. Okay, how should we do that? Any suggestions? Well, it's important not to think here, right? I mean, like, we could just do Lagrange multipliers and see what comes out. So let's do that. You might notice that, like, on your homeworks and everything else in this class, like, almost all of your problems boil down to, like, one of, like, 3 strategies. Like, apply your favorite theorem from linear algebra, or, like, drop in Lagrange multipliers and grind. And this falls into that category. So, unfortunately, the formula is not particularly nice, but it's a good warm-up, because the BFGS formula is even worse, and we'll do that in about 2 lectures. Okay, so the first thing I'm going to do is a slight change of variables. I'm going to say, instead of optimizing for j sub k, I'm going to optimize instead for a new object I'll call delta j, which is just jk minus jk minus 1. Obviously, if I know delta j, I also know jk. Okay, so in particular, what is our optimization problem then? Well, now it is the norm of delta j squared. By the way, I'm putting f because I'm lazy on the board, but I still mean Frobenius. Subject to, well, now we have to be the tiniest bit careful because there's a j, and now I don't have access to right? I need to, like, kind of, if I want jk, I really need delta j plus jk minus 1, right? But we can write it as follows, that delta j times delta x, which is like xk minus 1. What is that going to equal to? Well, it's going to be, if you think about it, f of xk minus f of xk minus 1. But now I need another term to account for the fact that I use the delta j instead of a j, right? So what I'll have is minus jk minus 1 delta x. Okay? Everybody see this change of variables? You're cool with it? Okay, so this is a vector, and it's kind of annoying. So let's give it a name. Any suggestions? About D for vector. Okay, because remember, these are all quantities we know. The only thing we don't know is delta J, right? So it's perfectly fine to just give this a name, deal with it later. Okay, so now it's not so bad. It's just delta J times delta X equals D. Incidentally, this is just a useful formula in your everyday life. You might not realize it now, but it is, which is just like, you know, what is the smallest change to a matrix that constrains it in 1D? This kind of formula comes up a lot. Okay, so what are we to do? Well, I would suggest writing down the Lagrangian, take its gradient, set it equal to 0, see what happens. Sound good? I think so. So what is the Lagrangian? Well, so it's a function of our unknown matrix delta J. And now we need a Lagrange multiplier. Notice that there's a vector worth of constraints, so we need like a Lagrange multiplier, which is a vector. We'll call it lambda. And that's going to be equal to, for whatever reason in the book, I didn't put a 1/2 here, so I'll roll with it. This guy, and then what do we need? We need plus the Lagrange multiplier dot product with the constraint, right? So delta J times delta X minus D. Everybody getting used to constructing Lagrangians by now? I think even if you forgot it in calculus class, this is a pattern in this class a lot. By the way, it's also just like a useful life skill, so like it's the one that I try to emphasize a lot. If you take my 6A38 class, then you do this, but you just like compute a million variational derivatives, because I think that's also a useful life skill. Okay, so so what do we need to do? We need to take the gradient. By the way, it's supposed to be a capital lambda, but my serifs got a little sloppy. Okay, so we need to take the gradient of this thing and set it equals to 0. In particular, the gradient with respect to delta J, right? That's how Lagrange multipliers work. So we have 0 equals the gradient of this thing with respect to delta J. Now, this is the norm of delta J squared, so pretty clearly the gradient of that, this is going to be 2 delta J, right? This is like kind of like the square. And then this thing is linear, right? So it's like the dot product between lambda and this complicated thing, right? But here's the delta J there. So if you recall from that little table of matrix identities we had before, you're going to get lambda delta X transpose. If you don't believe me, like a perfectly reasonable thing for these formulas, for example, if you're on your exam and you don't remember all these matrix calculus identities, for one, you can bring a sheet of notes. I'll send some information about that. But you can always just take the derivative with respect to one element here, and what are you going to get? You'll get the product of an element here and a product of an element there, right? Because it's linear. So you expect some expression kind of like that. Okay. So, yes?
For that case, like, I found 3 metric calculus, you know, like, weird transpose popping up and out all the time. Is it okay to, like, randomly?
It is absolutely not okay to randomly draw a transpose. You need to do the one that's correct. Like if I swapped lambda and delta X here, it would be a different expression. Yeah. But in this case, actually, both will give you the same dimension. So you're absolutely right that, like in general, if there's a formula you want to be true, it probably is, as long as the dimensions work out. But that isn't a proof. That's just like kind of a spiritual belief that math behaves the way you think it should, which is often true until it isn't. If you go to the physics department, it's always true. Yeah. Okay. But in particular, notice that this thing actually gives me a formula for delta J very conveniently. That's the nice thing about least squares problems, in case you haven't caught on by now. That delta J is equal to 1/2 times lambda delta X transpose. There's only one problem, which is we don't know lambda, so we're not done. Notice, by the way, already we have learned a very interesting fact about delta J. This is actually a really critical fact algorithmically. What is the rank of delta J? At most 1, right? Because it is the product of 2 vectors. Yeah. So really, like when we update delta J in this Broyden algorithm, we're doing very simple stuff. Yeah. That's not obvious from the way, like where we started, so we already learned something. Okay. But we need an actual expression or else our algorithm's kind of useless, so we're not done. Okay. But what do we know? No, right. So we remember we know that delta j times delta x is equal to d. So in particular, now we can plug in our expression here. We get 1/2 lambda delta x transpose times delta x, sorry, is equal to d, like that. Almost certainly. Yeah, did I forget a negative somewhere? Oh, yeah, I did. Yeah, well, you know, here's a negative. There you go. Turns out, actually, I think those negatives were about to cancel, but you got me this time, Paul. You're right, so there should be, yeah. Okay. But conveniently, if we kind of parenthesize this guy, notice that this is just the norm of delta x squared. Yeah? Notice, by the way, this had better be non-zero or else my algorithm is already stuck. So it's perfectly kosher to divide. And what we get is that lambda is equal to minus 2d divided by the norm of delta x squared. Cool? So if we substitute back into our formula here, what do we know? We know delta j is equal to minus 1/2 times lambda, which is minus 2d over delta x squared. All that times delta x transpose, like that. Obviously, the 1/2 and the minuses cancel, so this is the same as d delta x transpose divided by mod delta x squared. Cool? So isn't this cool? So the Broyden algorithm can happen in closed form. You see that? So the first thing you do, right, you have a new iterate x, you evaluate f at that point. That's enough for me to update j. And then to get the next x, I multiply both sides by j inverse, and then I kind of ping pong back and forth between j and x. Cool? So let's write that on the board or on the screen. So I'm too lazy to copy all the formulas, so we are going to operate on the screen now that we've decided we understand this formula. I can only assume because you guys aren't asking questions. Right, so we get, here's this formula for j sub k, right? This is just, this whole thing on the right-hand side is nothing more than delta j, right? This is exactly the formula on the board here, hopefully. Axel looks suspicious. Did I make another sign mistake? Oh, man. You're just looking inquisitive? Okay, that's fair. That's allowed. Okay, so we update the j, and then we can take a Newton step by just updating x using our usual Newton formula. And then we update j, then we update x, and so on and so forth. So does the basic algorithm make sense? We haven't filled in a few details, but like the high-level kind of iteration? Yeah. We do. That's absolutely right. I'm going to answer this two different ways. So one of them, I'm maintaining this matrix j. So like, great. In every iteration of this thing, I then have to solve I have to call Gaussian elimination and use that to get j inverse times f, which feels uncomfortable. I mean, if you think about it, like how much time algorithmically does it take to update j? It's quadratic time, right? In n, like in the dimension. But then you're going to have this cubic thing to solve the linear system. So wouldn't it be nice if we didn't have to do that? What was that? Axel has fantastic intuition. Maybe there's something we can do to make our solver a little easier, right? Because we know a lot about j. In fact, we just solved a linear system with a very similarly structured jk minus 1, right? Fantastic intuition. I want you to hold on to that for like 20 seconds. Okay, so beyond that, there's actually a different one, which is related to that. Which is how do we initialize j? There's no good answer there. Oftentimes, I think what people do is I just initialize it to the identity matrix, because we don't know any better. Incidentally, that feels like a hack, but it's actually kind of okay in the following sense. Let's say that j is the identity matrix. What will the first step of my algorithm be? Like, what is j inverse? Still the identity. And remember Newton's method is j inverse times the gradient. So in essence, if I initialize j to identity, what happens is my algorithm starts out by doing gradient descent, and then slowly starts to build up a Hessian and then kind of moves into that domain. To go back to Harry's question earlier, that's another intuition why this Broyden approximation is sort of okay, because in the dimensions where it doesn't know anything, it's just doing gradient descent. Yeah, it's kind of interesting. Okay, so anyway, this is a common choice. I think sometimes people will like spend a little time doing like divided differences or something for the very first J, but that seems relatively uncommon. But there's still two more problems, sadly for us. One, as Axel points out, like algorithmically, this is very expensive. Every iteration of this thing still takes cubic time. I got to invert J. Yeah. Moreover, there's this memory issue, which I illustrated on the board and so cleverly erased, which is the fact that J contains remnants of like a million iterations ago, right? Like I just keep updating J. I never like throw it away and clean it out, right? Both of those are problematic. So that's what we're going to address next. In other words, like this thing has a long memory, so like the approximation J really might not be such a good one, especially if Newton is taking big steps, right? And we have to invert J in each step. So in order to do that, remember this is our favorite update formula, but it's a little bit complicated, so let me write it in a simpler way, which is this, that like there's some vectors u and v that I can just gather from this expression here, and really like the core of this update looks like the following. Okay? So here's an idea. Let's say like this is actually one of relatively few times in this class where I will allow you to store the inverse of a matrix. This is typically not allowed, but you get licensed for about 2.5 lectures. So let's say that I knew jk minus 1 inverse. Question is, can I update that to jk? Anybody know the answer to this one? This is a bit of a linear algebra trivia. I don't know if you've encountered this before. Ah, that's too bad. There's a really famous formula out there, which is maybe it's one of these things that's very famous in numerical analysis, but actually outside of our community, nobody cares. But in case you didn't know it, you'll know it now, which is the following. This is called the Sherman-Morrison formula, and it's this. It is precisely what we wanted. It says that let's say that I know how to invert a matrix A, and what I'd like is to add UV transpose to it, and I want to know what the inverse of this thing is. And it turns out, you can actually write it in closed form. It is itself a rank 1 update of A inverse. Okay? I don't think we're going to bother proving this formula on the board. Literally, the proof here is you take the left hand, like you take the two things, multiply them together, and show you get the identity. Right? Like if I want to show that one matrix is the inverse of another, I just multiply the two and get I. And that's just algebra here. Like hopefully you'll trust me on that. Or if you don't, then like just do it on your paper. But right, so this is precisely what we wanted. Does everybody see that? Like this tells us. So now here's the really magic trick in Broyden's method. In fact, we don't have to store J. In every iteration, what we're going to update is J inverse. Now, why is that kosher? Remember, I told you guys that a totally reasonable choice for the initial J is the identity matrix. Why do you think is the real reason people do that? Well, it's because we know it's inverse, right? It's also the identity matrix, yeah? So in particular, here is an equivalent algorithm up to numerical precision, of course, which is the following. Rather than using J, I'm going to always store J inverse, and then at every step, instead of updating J, I'm going to update J inverse using the Sherman-Morrison formula. Okay? So remember, every iteration of Broyden's algorithm before took cubic time because I had to solve a linear system. Now how long does it take? Quadratic, right? Because I have to do a matrix vector multiply. Technically, I guess less than quadratic, maybe. No, actually, no, it's quadratic for matrix vector. Yeah. Okay, so yeah, so that's the trick. Any questions about that? Isn't that sneaky? I think it's a really sneaky trick. This Sherman-Morrison formula is just like a useful like life hack. It shows up a lot. Yes? That is a great question. Like, why is it okay to split the inverse? The short answer is it's not. But I think there's like sort of a few factors at play that make it like okay-ish, which is that the usual problem in storing inverses of stuff is you're like basically dividing by 0. You get giant numbers. But since we're using the secant approximation anyway, like I think somehow these things kind of balance out. Like you're dividing by these positive differences, and so somehow it's like not quite as ill-conditioned as it could be. But you're right, it's a problem. And there are cases where this algorithm blows up. Especially, I mean, like that actually more or less corresponds to when your Jacobian is singular, which is exactly when root finding is hard, right? So like somehow, yeah, everything conspires against you. When root finding problems are hard, root finding problems are hard. But people are often willing to forego that for algorithmic efficiency. The other reality is that oftentimes people use procedures called line search in root finding, and more even in optimization, where like rather, like so in Newton's method, you just like jump to the minimum of the quadratic. A more typical thing to do, or rather the linearization, I'm getting ahead of myself, is to like draw a line between that point and the current iterate and kind of search along that line for a root, or like something closer to a root. If you use those kinds of procedures, then like the search direction, like J inverse times delta, whatever it is, F, might not matter quite as much because you still have another procedure that wants to find a root kind of hiding in your algorithm. So the reality is in a lot of these things, there's a lot of wiggle room. But these are all excuses. You're absolutely right. This is an ill-conditioned thing. And you can actually see it in the Sherman-Morrison formula, by the way, which is notice there's a denominator here. And you don't want to divide by 0. So in particular, notice that there's like a few cases where that can't happen, namely if A is positive definite, for example. But in root finding, that's A is unlikely to even be symmetric, despite what your TA says. I get to tease him because he's my grad student. It's actually part of the contract. Okay, yeah, so that's that. The other thing that I think we're not going to cover in great detail is the fact that J can get kind of stale. Remember, it like, like an elephant always remembers, like so does your Jacobian from Broyden's method. Never mind. The like Broyden's method, the Jacobian is building up literally all of your previous iterations into the current one, right? And you can imagine a case where like the first couple steps of your optimization like took you very far in Rn, and so those divided differences are like really bad news, right? One thing you can do is just every once in a while reset J, just throw it out and replace it with the identity, and that's actually completely kosher. People do that. Unfortunately, that adds a parameter to your algorithm. You have to like decide how often you should do that. But there's a second trick, which is I think the more common thing to do, which is called limited memory Broyden algorithm. Sometimes they just say L Broyden, I think. I think the more common one is LBFGS, but we're not there yet. And so here's the really cool idea that I'm going to just sketch out in words, and I'll let you think about it at home because we're a little low on time. I can apply the Sherman-Morrison formula more than once, right? So in particular, let's say that I remember the last 5 iterates of my algorithm. So I remember all the X's and all the F's. Then I start with A0 equals identity, and I basically use this formula 5 times over just recursively. What I'm going to get is the Jacobian after the 5th iteration, right? So here's a really weird way to store J5 inverse, is to just store the last 5 iterates and construct it on the fly. Yeah? And that is what limited memory Broyden algorithm does. It always stores a fixed number of previous iterates and then says, I'm going to assume that J was identity 5 iterations ago. But there's like a sliding window that happens here. And it builds up that approximation just from the last few and then inverts it. And if you parenthesize the expression just right, you can do it all with matrix, with vector-vector multiplies. You never actually need to build an n by n matrix. So anyway, if you're curious, there's a little flag that you can often enable in code for these algorithms where they say limited memory. And that's what it does. It swaps from remembering A inverse here to just remembering the constituent parts of A inverse for some sliding window. And that's the thing that you can apply very efficiently. That would be a good homework problem, would be deriving that formula. No, it wouldn't. That's a really tough homework problem to get right.
Which one?
So like you can either build up, like you could build up J, you could build up J inverse, or you could work out the right piece of code that recursively does this with vector-vector multiplies, and they should all agree if you did it right. That would be, I think that's like a good software engineering task, but maybe not a great numerical analysis problem. Okay. So in any event, that concludes our discussion of root finding. Any questions before we move on to optimization? Is it hot in this room, or am I just having a meltdown? Okay. Great. Love that. Okay. Fantastic. So our next task in 6S955 is to move from root finding to optimization algorithm. And there's a very obvious reason why we go from one to the other. Remember calculus? So why do you, what is one of the main reasons that we compute derivatives? Well, remember, it's to compute minima of functions, yeah? And so if you remember back to your like high school calculus class or college or whatever, middle school for some of you, because I'm elementary school. What did you do? You said like there was like a thing you're programmed to do from birth, which is I hand you a function, you take its derivative and set it equal to 0, and then you solve that system of equations and give back the 0 and call that the minimum. And why are we able to do that? Well, essentially what we've shown in calculus class is that the minima of a function, and by the way, the maxima and the saddle point, are all contained within the set of critical points for our function, right? And so root finding and minimization are very, very closely linked, at least for differentiable stuff. Okay. So I love optimization. I can talk about optimization well, literally for a whole semester. We have many courses on optimization in this department that focus on the thing that we're going to do in like 3 lectures. We're going to do it a bit from a numerical methods perspective, meaning that we're less concerned with like a giant hierarchy of different optimization problems and their theoretical properties, and more about coming up with just generic sledgehammers like Newton's method that can just take a generic function in its gradient and give me something approximating a minimizer. As you can imagine, we expect to do a lot worse on that problem than on these beautifully structured problems that you'll encounter in the operations research department, right? Like linear programming or cone programming, whatever. And we actually already have done a lot of that, right? I mean, I think that optimization is just this valuable language to become fluent in as you become mature computer scientists in 2023. I think there's so many different computational problems whose output is a set of real numbers that you can understand as optimization, right? Like, you might have noticed that basically everything we've done in this class so far can be written that way, right? So here's some examples of objective functions for least squares. It was, the norm of ax minus b. We did projection. We did eigenvectors as critical points of x transpose ax subject to a constraint. Principal component analysis. Even the Broyden's algorithm we managed to pose in terms of optimization, right? So clearly this is a really powerful language. Moreover, sometimes we need to add constraints to these problems. For example, some of the ones we've seen here. Right, so essentially now, what we're going to do is move away from these problems which are really beautiful structured, right? Like least squares. I don't need a generic optimization problem to solve it because there's very specific techniques out there for doing that. To ones where I just have some function f and its derivative and I want to make it small, right? That's our task here, right? And so in general, I think many of the things that we see in this course we really can think of as a sort of variational approach to problem solving, where we cook up some energy functional or some objective function that measures all the things that we want to be true when our function is small, and then we minimize it, right? And arguably that's just like a huge part of computational modeling in 2023, so it really is worthwhile to study all kinds of algorithms for solving this. Yeah? And I'm guessing any of you guys that have taken a machine learning course, basically at this point, machine learning and optimization have slowly kind of converged to the same object, right? Like you spend all this time analyzing algorithms like gradient descent, which is nothing more than first order optimization technique. But of course, the story often stops there, but the reality is there are many algorithms out there, and the algorithms that are really fantastic for these large-scale learning things are not always great for computational problems in other domains. Okay, so here's our motivation. Essentially, so far, every one of our optimization problems has had a closed form formula for how to solve it, right? Like least squares I could do with a linear system, but what if we're not so lucky and we just have access to our objective and the derivatives, what then? And so for instance, for root finding, we did exactly the same thing, right? I was given access to f and its derivative, and my job was to find its 0. Okay, so for today, we're going to just focus on unconstrained problems. So we're going to put no constraint on our unknown x. It could be literally anywhere in Rn. In fact, for today, we're only going to do this in one dimension. But of course, there are many different problems that fall into this. The book goes through many of them. One very simple example is fitting an exponential to data. So here maybe I indexes data points, right? And so an exponential function is like c e to the axi. So a very simple way to fit my data would be to compute the prediction of my model, like c e to the axi, compare that to the actual y, square, and sum over my data set. Sadly, this problem is nonlinear, thanks to that exponential. Right? If I want to be more modern, then instead of an exponential, I put a neural network and its weights, but it's basically the same. I still want to find the minimum of this thing. One thing to realize here is the minimizers with respect to c and a, right? Not with respect to x. Okay? Or similarly, like the book, maybe we'll skip over the details here, walk through a few other examples. Another is maximum likelihood estimation, where like I'm trying to fit a Gaussian to a data set. So I do so by like a Gaussian is parameterized by its mean and its covariance. So I evaluated it on all my data points, and I want the probability of observing my data to be as high as possible. So now I need to optimize that thing, usually the negative log likelihood. And we also, just because I'm a geometry guy, threw in one additional one of the book, which is a median problem. This is kind of a fun one because it's not differentiable. In particular, like there's sort of an absolute value looking function hiding here. There's a fun geometry problem, which is like, what is the proper analogy of taking the median of a set of numbers if you're in more than one dimension? I'm happy to get excited about that in this class and waste a bunch of time telling you fun properties of this problem, but instead, why don't you take a look at the book if you're excited about this. So this is all to say that there's a lot of optimization problems out there in the universe. I think all of you guys coming from different corners of our department have encountered this in your own domains. Hopefully I'm not wrong. And since you guys never participate in class, like the good news is I'll never know. Okay, excellent. So as usual, we're going to talk a little bit about sort of what we're looking for. Like what does it mean to declare victory on this problem? And then we'll derive some algorithms. We're going to start again in one dimension, and then in future lectures go to higher dimensions. We'll see if we manage even with one dimension how far to get today. Okay, so first we need to establish some ground rules. Like what are the objects we're trying to look for? And I think a lot of this is stuff you're used to from calculus class already. So for example, when we talk about optimization, very typically our objective functions might have many minima, locally speaking. So for example, here I have one local minimum and one global. And in different problems, we're looking for one or the other. And unless our problem is very nicely structured, the best we can probably do is hope to find a local min, right? Like by walking downhill. Now there are exceptions to that. Convex programming is the most famous one, right? Where essentially I just say, I'm only going to work in the space of functions that don't have local minima, so I don't have to worry about this issue. But in the algorithms that we talk about here, and in many machine learning techniques these days, like deep networks are wildly non-convex, typically we're just trying to find a point where the objective is small, not necessarily the smallest objective, right? A few definitions, just so we're all on the same page. I think it's pretty easy to essentially formalize the picture on the previous slide mathematically. So for example, the global minimizer of a function, x star, is a point x star where if I evaluate f at x star, I get a smaller value than evaluating it anywhere else. I stumbled through that sentence, but hopefully you guys got the spirit of it. And whereas a local minimizer kind of says that like in some little tiny ball of x star, that relationship is true, but if I go outside of that ball, I can't say anything. Okay. Now, of course, we often take the derivative and set it equal to 0 to establish optimality, right, or to find possible minimal points. I think one thing that we often forget, because we just take this for granted, is like, why is that strategy okay? Like, in particular, the first algorithm everybody talks about for optimization is gradient descent, which is predicated on the fact that the gradient points uphill. And I think actually one question that sometimes gets a little bit lost in the story is like, why is the gradient the direction of steepest descent for a function? It's a totally reasonable question to ask. There are a lot of different arguments for that. Here's a very simple one. Let's say that I take a function that's differentiable f of x, and I approximate it with a Taylor series about some point x0. Fun fact, it's actually part of my MIT contract that I have to write this formula at least one day, once a day. Okay, so there's a coarse approximation of f near x0. So let's say that, first of all, let's say this is not equal to 0, so my gradient is non-zero. Can I be at a local optimum? I mean, that would be bad news. Like, intuitively, our answer should be no. But I think it's important to like actually think about this critically for a minute. Yeah. If it's, but this is sort of the opposite situation. So I'm telling you the gradient is non-zero. Yeah. Then like, why am I not at a local optimum? Yeah, and like in particular, we can be formal about that. Like notice that if I take, for example, this thing to be minus gradient of f at x0, right? Then what do we have? That this is a negative number, strictly negative number. So I can move in some little infinitesimal thing, maybe like times alpha for some small alpha, and f gets smaller. So necessarily, if my gradient is non-zero, I cannot be at a local minimizer of this differentiable function. This is predicated on being differentiable, by the way. Okay. Notice that that's all we've shown. We haven't shown that it is a sufficient condition, because it's not. Right? So when we do this strategy of setting a gradient to 0, we still have to check that what we got was a minimizer. We've shown that the set of minimizers is within the set of things where the gradient are 0. Right? But in any event, that's one thing. The next thing you might do, just to kind of like make sure that the intuitive language we use a lot is actually borne out mathematically, is we talk about the gradient, or really minus the gradient as being the direction of steepest descent, and plus the gradient as being the direction of steepest ascent. How can I see that in this linearization formula? I think it actually like takes a little second to think about, right? Which is kind of funny because I feel like we all take that for granted. What was that? Yeah, Paul has the right intuition. Like if I move in the gradient direction, I feel like the function should increase. In particular, like I can move in whatever direction I want, starting at x naught. So let's call that direction maybe delta, like that, right? And this value here, this is the change in f as I move in the delta direction. Notice that in particular, if I take the absolute value of this thing, this is the absolute value of a dot product. It is screaming out for a particular inequality. What is that inequality? The other one. It's related to the triangle inequality, at least in L2. What was that? I think you got it. It's the Cauchy-Schwarz inequality. That's right, Paul. It's the Cauchy-Schwarz, and it says the following, which is that is less than or equal to the inner product, or rather the product of the 2 norm of grad f and the 2 norm of delta, with equality when these two vectors are parallel and like positive multiples of each other, right? Notice that that actually implies that the direction of steepest ascent is necessarily to move parallel to grad f, right? Because otherwise this equality becomes strict. Yeah. So anyway, like when we talk about the direction of steepest descent and ascent, really, you can get all of that from Cauchy-Schwarz and Taylor series, and I think it's important to like remember that these are not like fancy mathematical theory. It really is just a byproduct of derivative formula. Okay. So in any event, that's what we've shown, that essentially if grad f is not 0 as a local optimum, so oftentimes when we do optimization, what we really end up doing is actually just root finding on this particular expression, right? So notice that all the algorithms in the last lecture and earlier today actually apply to optimization because it's just root finding on the gradient. That make sense? Right. No. So really, I think you can understand a lot of optimization problems as the following: they do root finding on the gradient, they find a critical point. Of course, there's some nice structure we're going to use here that shows that Broyden's probably not the best thing to do here. But you could use Broyden. That's perfectly fine. Try. You need to actually check they're at a minimizer, and then maybe repeat. How could I check if I'm at a minimizer? Any ideas? Yeah, I could, for one, I could like take a few small steps, see if the function increases. Let's say I take the limit as those small steps get really small, then that suggests I use calculus. Look at the second derivative, the Hessian, right? So in particular, if we have this Hessian matrix, right? This is I'm dredging up all this terrible stuff you don't remember. Right? I add a term to my Taylor series times the Hessian times x minus x0, right? So at a critical point, this term goes away. So now the dominant perturbations are this guy, right? So if I want to be at a local minimizer, if you look at this expression, if h is positive definite, notice that makes this number positive, which is good, right? It means if I displace away from x naught rather, my function has to increase in all directions, meaning that I'm at a local min. Yeah. This is just some calculus review, really. Yeah, so here's our notation, and indeed we have a bunch of these cases. If h is positive definite, I'm at a local max, or min. If it's negative definite, I'm at a local max. If it is indefinite, so I have like some positive eigenvalues and some negative ones, then I'm at a saddle point. And what if H is not invertible? It's got some zeros in there. Like it's technically has eigenvalues that are all greater than or equal to 0, for example, but some of them are 0. Then I can't say anything at all, turns out. I need to use some other condition to check if I'm optimal. But lucky for us, that condition is pretty rare. Okay. Of course, checking for optimality this way is expensive. I have to compute a big Hessian matrix. There are other things we can do. I think a big pattern in computer science, especially in the last 10 years, is to structure a function in such a way where if I find a critical point, I know that it is optimal, right? So in other words, like put some condition on f so that I have, there's no such thing as a local optimum. So a very common condition for that is something called convexity. I spend a large part of my everyday life worrying about convexity. And all of you should too. And in particular, convex functions are sort of bowl-shaped. They satisfy this inequality on the screen here, which says the following, that like if I take the value at 2 points of my function, and I linearly interpolate between them, right, that's this line here, then the function values themselves, they don't have to lie along that line, but they lie underneath it, right? And so by that property, your function cannot have a local minimum. So let's see what that would look like. So let's say that I have a local min like that, yeah? And now I choose the 2 local minima. Notice what happened, f lives above it, above this line here. So I'm violating that convexity property. Does that make sense? By the way, fun trivia question. So, convex problems. I think computer scientists, we say convex and you think easy, right? You think like, oh yeah, convex problem, so like we're good, we're done. There's like all kinds of software out there for that. And it's sort of true, like gradient descent or whatever, under pretty weak assumptions for a convex function will converge to the optimum. Does that mean that they're easy to optimize? Even from like a computer science theory perspective, like for example, from an NP hardness perspective? The answer is actually no. There are convex problems that are NP hard. And even with polynomial numbers of variables. So if you want like a really interesting theory thing to Google later and like really mess up your brain, here's a fun one. It's called copositive programming, which feels very innocent. So this is a very common thing that like if you take an optimization course in this department, you'll almost certainly cover, which is something called semi-definite programming, where my variable is a matrix and I make a constraint. I say that my matrix X maybe is symmetric, and we use this funny inequality notation like that, which is saying that all of the eigenvalues of X are non-negative. And this is a convex set. If I average 2 matrices, if I take 2 matrices and I take their average, and both of them have positive eigenvalues, you can show that the average does too. Yeah, this is an easy thing to check. Let me define for you a different set of matrices, which is the following. This is a set of matrices X that satisfy the following. By the way, you can make it symmetric. That's perfectly fine. I take any vector z transpose xz is greater than or equal to 0. Now, if I said for all z, that would be semi-definite, right? But let's say I do this following. For all z, which itself is greater than or equal to 0. This is a bigger set than the set of semi-definite matrices. Checking if a matrix is in the set is NP hard. Or I think it's worse than that, actually. Which is weird, because this is a convex set, right? Like, so, like, for example, computing distance to this set is a convex problem. But actually solving it is quite difficult. So anyway, if you like this kind of stuff, this is way outside of the scope of this course, but you can Google for it. This is called copositive programming. And there's some very brave optimization people out there that try to tackle these problems. In my mind, this is one of these ones where, like, if I can take a problem and reduce it to this, then this is like one of these like abandon all hope, all ye who enter here kind of situations. Like, oh God, like I don't want to get anywhere close to that. Okay. So anyway, this is my little soapbox to just say convex means a very particular thing, which is I can't have a local optimum, which is absolutely true. I can't have like 2 matrices in a set and a matrix in between them, which is not in a set. But that doesn't make it easy. I think this is a common misconception. It's also a misconception that the only problems that have this property, that local optima are global, that necessarily means convex. This is one of many. So here's another example, which is quasi-convex, which actually weakens the property we had before. It says that if I take the value between the midpoints somewhere, right, it doesn't necessarily have to lie beneath the line. It just has to lie instead underneath the max of the two values that I've evaluated. This is called a quasi-convex function. And you can also check pretty easily that there can't be local optima in quasi-convex programs. The reason that we don't work with quasi-convex problems then is that like they don't have a nice algebra. So like if I take two convex functions and I add them together, I get another convex function. And so there's like this nice set in algebra that we can work with that kind of suggests a whole programming language approach to optimization. That is not true here. In fact, you can see it with this very function, right? If I add two of these where I put the dip at two different places, I'll get something that's not quasi-convex. Yeah. Okay. Does our problem make sense? The input and the output? Okay, fantastic. So let's quickly cover two one-dimensional algorithms. I'm going to see if I can do them both in the remainder of today's lecture. We'll see how far we get. One of them is really simple, Newton's method. So we already covered Newton's method. But now, rather than doing root finding, we're doing optimization. But we argued that that's exactly the same as root finding on f prime, which means that immediately we have an algorithm for optimization. There it is. So if I want to do root finding for Newton's method, I do f over f prime. But now I want to do root finding on f prime, so I have f prime over f double prime. Does that make sense? If we're looking for an alternative way to understand Newton's method, notice that like one way that you could understand it is like I have my objective function, whatever it is, I approximate it with a parabola, and I minimize that parabola. That's one way to understand what this algorithm is doing. But conveniently for us, it's a one-liner because we already did all this stuff in the last lecture. Okay. One thing I'll let you guys think about, we're not going to cover now. After we did Newton's method, we also talked about secant, right? And secant basically took f prime and it approximated it with a divided difference. Now we have an f double prime, so it's actually not clear how to take this algorithm and make the secant version of it. There are some crazy things you can do for that. So one of them, for example, is a technique called successive parabolic interpolation, where you take the last two iterates and you fit a parabola to them, and then you use the first and second derivative of that parabola as f prime and f double prime. I think this is not a very common algorithm in practice, but it does exist. Okay. Any questions so far? This is an easy one. But notice that if I follow the story of the previous lecture, I just cheated, because I skipped over a thing. Remember, we actually didn't start with Newton's method. We started with bisection. And so I think there's a totally reasonable question in 1D, which is what we'll answer for the rest of today's lecture, which is how do we make a bisection-looking algorithm for optimization? And it's not entirely obvious, right? Like, if I take a function and so here's like even a very nicely behaved function, and it's like bowl-shaped, whatever, and I tell you there's a minimum somewhere between these two things. Maybe I evaluated at the midpoint. I don't think it actually tells me a whole lot about what side the minimizer is on. Like, for all I know, this function does that. Yeah? So it's not quite so easy as root finding. In other words, like basically what I don't have anymore is this intermediate value theorem, right? Like I don't have an easy condition to check whether there's a minimizer. But it turns out there's sort of a similar condition we can put on functions that's a little stronger than continuity that does lead to such a thing. And this only works in 1D. This is kind of a little bit of a trivia thing, but I do think this algorithm is kind of fun, so it's worth the 20 minutes left in class, which is to look at unimodular functions. This is sort of like the analog of continuous functions for purposes of optimization in 1D. If you ask me what this has to do with totally unimodular stuff, I would, leading programs, I'd get confused. But I digress. A unimodular function has the following property. So it's a function on the interval from a to b. And it basically says that there's some point x star. There it is. You might notice x star happens to coincide with the thing we're looking for, where f is decreasing for any x less than x star, and it is increasing for any x bigger than x star. Okay, so notice that the unimodular functions include, there are discontinuous unimodular functions, right? So for example, that function is unimodular. Like they don't have to be differentiable. They can be all kinds of weird stuff. They just have to have this one property that they decrease and they increase. Right? Notice convex is an example of such a thing. Okay, so I claim that we can make a bisection-like algorithm for unimodular functions. This is kind of fun. So here's going to be our trick. I'm going to erase my diagram because there's too much going on. Continue the same pedagogical philosophy that, like, the bigger you draw the diagram, the more likely the students understand. Yes?
Why is that the step thing just really why is that unimodular?
Ah, well, if we have sort of a weak notion of decreasing, which is that it's not increasing. And so in other words, like, if decreasing means when I go to the right, the value only can get smaller.
But there's no point on that where it's increasing directly.
Yeah, in this case, x star is non-unique.
Oh, wait,
yeah.
But I guess being equal, it's not strictly increasing.
That's right.
Okay, that's the point.
Fantastic. Okay, so let's draw ourselves a unimodular function. There's one. Okay, and moreover, let's make a bracket like this. Okay, so here's going to be our trick. I'm going to evaluate, now in bisection I just evaluated at 1 point. Let's say I actually evaluated at 2 more points. So maybe this guy and that guy. Okay? So. I claim that we can always discard one of these two intervals. So in particular, here's a little theorem about a unimodular function. So let's give these things names. So we're going to call this A and B and x naught and x1. Okay? So what we're going to do is compare the value of f at x naught and x1. Sorry, this diagram is getting a little complicated. Hopefully you can follow what's going on. So if f naught is bigger than x1, that's not the case here, then the first thing applies. So here we have the second one. So if f of x1 is bigger than f of x naught, right? So this is case 2. Well, in that case, what do we know? We know that if I take any other x, where x is between x1 and b, so we're going to take x in this interval, what do I know? Well, in particular, the value of x has got to be bigger than x1, right? So the optimum can't possibly live in that interval. Cool? So these are kind of useful little facts. I can always, if I take my interval and I divide it into 3, there's always some part of that interval that I can throw out. By the way, these conditions, I always get them wrong. I have to like logic through them every time. Somehow they're like hard to keep in your head, but if you draw pictures like this, you'll remember. Okay. Right. So notice that this immediately suggests a bisection-like algorithm, maybe trisection, right? What do? I take my interval, I divide it into 3. I check this condition. One of these two things has to be true. And then I remove either the leftmost or the rightmost of the 3 regions, and I recurse. Yeah? So in other words, instead of bisection, I now always remove a third of my interval. Yes? Why don't I take x naught equals x1 in the midpoint? Or wherever. Ah, well then there are no useful comparison principle here. It's not clear what like left to right means here. I think in this case you end up with like these two conditions become trivial. I'll let you check that one at home. I'm gonna get it wrong. I think probably what needs to be, what was that? Yeah, this is like I'm 100% confident that you can't do that, but if I try to convince myself now, I'm gonna get lost in symbols. But certainly these properties are true. So version 1.0 of our algorithm is called trisection, where I just divide into thirds. I always throw out 1/3 of our interval, and life is good. That's perfectly fine. That'll do it for unimodular optimization. But I claim that we can do better. And here's a really sneaky trick. This is such a beautiful, cool, clever algorithm. Okay, so here's the thing. This requires evaluating the function twice in each iteration, right? I divide my interval into 3 parts, and then I have to evaluate it here and here. Okay? So I claim we can get away with one function evaluation. We can make our algorithm I want to say twice as fast. It turns out that's not entirely true because the convergence will be a little slower. So somewhere in between. Here's going to be the trick. Let me erase this picture here, and instead draw you the following picture, which is just the interval from a to b, like that. And just for fun, I'm going to take a to be 0 and b to be 1. Obviously, I can always take my function and kind of rescale it, so that's the case. Okay, and I'm going to make one conceit, which is I'm going to choose x0 and x1 in a symmetric fashion. This is just, I didn't have to do this, but like I certainly can. Like this is an algorithmic design choice. So in particular, I'm going to make this interval equal to a constant alpha, and this interval equal to a constant alpha. So maybe one way to view that is that I'm going to stick x0 at the location alpha, and x1 at 1 alpha minus alpha. Right? So far we've taken alpha to be a third. Right? Does that make sense? So let's say that I discard this interval here. Okay, so now in our next iteration, I tried to draw this picture in my notes and it got really messy. We're going to see if we can do better. Probably not. So here's our next interval. Okay? But notice that like x0, that's still inside of the interval in which we don't know anything. Right? Okay, so here's going to be our trick. Oh no, I already got it wrong. No, I didn't get it wrong, but my diagram is going to be annoying. We're gonna edit our diagram a little bit because my job is to confuse you guys as much as possible. Okay. In particular, I'm going to make a larger choice of alpha, and you're going to see why in a second. Yeah, this would work out, but it's going to be messy. This is purely for aesthetic purposes. I'm going to erase this diagram. I'm so sorry. In fact, I won't even erase it. I'll do it here. I'm going to make my interval really wide. I'm going to make my alphas way closer to the center. Okay? I'm going to leave that there because that's the dead remains of my old diagram, and I should feel guilty for the terrible things I've done. Okay. But right. Okay, so now I've got this interval here. Like that. This is alpha. Okay? So far our diagrams are the same. But I purposefully chose a bigger alpha because I kind of wanted this thing to end up on the right-hand side of this smaller interval. And over there ended up on the left. And that turns out to be not as nice. Okay? That's what I did. Okay, so this is still 0. This point is 1 minus alpha. Here's going to be our trick in our recursive subdivision of our algorithm. I'm going to choose another point here on the left-hand side and make this the x0 at the next iteration. So here's going to be my trick. So this is x0 prime for the next iteration, and I'm going to call alpha x1 prime. Is that kind of cool? So in particular, the question is, what is alpha in order for this to happen? Yeah? I'm going to double check my math so far. Well, what do we know? Okay. So this guy's equal to alpha, but notice, like, let's think of alpha as the fraction of the interval that I've inset. Then in particular, this alpha also has to equal a different thing, which is this interval is 1 minus alpha times the width of the full interval. Does that make sense? So in particular, it is 1 minus alpha squared. Okay? So now we have a little system of equations to solve, which is the following. Alpha equals 1 minus alpha squared. If this is true, then I have this beautiful picture where, like, when I chopped off that right part of the interval, it ended up like I just swapped x0 and x1, and I only have to evaluate my function once on the other side. Isn't that cool? Luckily for us, this is a thing we can actually solve. Right, so this is 1 minus 2 alpha plus alpha squared. So in other words, 0 is equal to 1 minus 3 alpha plus alpha squared. And by the quadratic equation, we will get that alpha is equal to 1/2 3 minus the square root of 5. Turns out the other root is not between 0 and 1, so that's not a good choice of alpha. Okay. So, anybody recognize this number? This is numerology is about to happen here. This is like Britney Spears and the Kabbalah and all that. Yeah, this is the golden ratio. It's like once again, we've ended up with this magic number, tau, almost actually. It turns out that 1 minus alpha, alpha is equal to the golden ratio. Oh no, is equal to tau. So it's like the width of this part of the interval for whatever reason. Okay, so in other words, our algorithm looks something like this. So here, I've purposefully drawn a weird looking, but still, what do you call it, a unimodular function, right? So in my first iteration, iteration 1, here's A, x0, x1, b. Fun fact, in order to draw this diagram, I really did have to work out the golden ratio and plot these things in the right places. Otherwise, it just doesn't work. So in the next iteration, notice that like, because this value is bigger than this one, I can effectively throw this entire interval away. So what does that mean? Well, that means that now I'm going to put b at x1. I'm going to swap x0 and x1, and now I just need to insert x0. So I only have one function evaluation for the next one. Similarly for iteration 3. Then iteration 4, I end up throwing out the left-hand side of the interval, so now the label swap goes the other way. Okay? Isn't this beautiful? So every step of this algorithm ends up taking one function evaluation instead of two, like our trisection. Yes? Probably. You're right. Tau is like 2 pi, right? Yeah. Oh. I'm going to call it tau. Okay. That's absolutely right. So right. So we chose this particular choice of alpha by kind of making the two things share the same value. That led to this quadratic condition, and that's the golden ratio, which I'm calling tau. But apparently it's actually phi. But I thought phi was the one with the Euler or something quotient function. Oh, there's only so many Greek letters, you know? What was that? Right, exactly. You know, it's the speed of light. That's a lambda, I think. There's too much of this stuff. Yeah, so this is a particular algorithm for optimization for unimodular functions. It's called golden section search. But by the way, notice that like in the local neighborhood of a local optimum of a function, your function is unimodular. So long as like you can like reasonably bracket them in, that this thing can be applicable. And it's kind of sneaky. So essentially, I very carefully evaluate my function at these two inner points. And then I have to do this kind of clever exchange of x0 and x1 recursively to shrink down my interval. Each time I do that, my interval becomes slightly smaller by a factor of tau, whatever that is. Notice that tau is not 1/3, and it's not 1/2. So like the convergence rate, the constant factor in there is like kind of a weird magic number. But it does outperform trisection if you work out the ratios. That really is. Any questions about that? I always get nervous explaining this algorithm for some reason. I feel like it's really hard to get the diagram right. Yeah, so this is our, I think, sort of as close as you can get to the bisection algorithm for root finding when you want to do optimization. And it requires a pretty strong precondition, this unimodular situation. And moreover, it's still not terribly efficient. Notice that the convergence rate here is linear, right? Because ek and ek plus 1 are constant ratio of each other. Fantastic. So we're done a minute early, so that's totally fine. In our next lecture, we will talk about optimization in more than one variable. So our very first thing, unsurprisingly, will be Newton's method. And then we're going to try and do Broyden's method. But going back to Chris's question earlier, like, remember that now in Newton's method, and here's the thing I want you guys to think about over the next couple days. I know you're going to think very hard about it. You're promising me. I can see it in your eyes. Yeah, where's Newton's method? I'm sorry. Yeah, this guy. Oh, no. OK, there's Newton's method. Right? So in multiple dimensions, this is going to end up being like the Hessian of f times the gradient. I guess inverse. Let's say I wanted to do Broyden's method. So now the matrix I need is the Hessian. It's not the Jacobian anymore. Right? My question is, does Broyden's method make any sense? The answer is kind of no, right? Because the matrix is not symmetric. The J you're likely to get. So if you want like a really fun algebra problem to work out before our next lecture, it's add the constraint that J transpose equals J and then work out that same optimality condition a second time. And that will lead you to a particular technique called Davidon-Fletcher-Powell. Fun fact. Okay, so in any event with that, you guys have a lovely weekend. It's Thursday. And I will see you guys on Tuesday. Don't forget to study for your midterm. Chris doesn't know it, but tomorrow in his section, he'll hold a midterm review.